All right, guys, welcome to lesson 9.1. We're going to be talking about logarithms in this unit. So today we're going to talk about what a logarithm is, and then we'll talk about how to evaluate basic logarithmic expressions. That means you should be able to simplify them and figure out what they equal. So let's begin. So what I'd like you guys to do here is to take a look at this and go ahead and do it on your calculator yourself real quick here. So you guys know how to do this one already. So like for instance, for 10 to the x equals y, I'm telling you x equals -2. So just get out your calculator and type this in there and see what you get. And whatever you get, you're going to put your answer there. That's pretty self-explanatory. Over here, this is new. You all should have a log button on your calculator, and sometimes you have to enter the number first. So if you wanted to find log of the first one, which is 0.01, sometimes you'd have to enter the number first and then push log, or sometimes you push log and then the number. You'll just have to experiment on your calculator to see which one works for you. But go ahead and do that and then fill in these tables, and then when you pause the video, I'll show you the solutions and we'll talk about what the results mean. All right, and so this is what you should have gotten by doing that. And hopefully something's catching your eye here. It's the fact that these two tables are exactly the same. It's just that for this one, its x values are the y values of this function, and vice versa. The y values of this function are the x values of this function. And this is actually a topic that we've already talked about this year. Anytime you have a function as an input and output, let's say of a and b, if you can find another function who has the same inputs and outputs, but they're just swapped, that's what we call an inverse function. And so it's been a little while since we've talked about that. I think it was back in September probably. But that's what an inverse function is. An inverse function is a function where for this one, if you plug in -2, you get 0.01. Well, on this one over here, you plug in 0.01, you get 2. So that's what they are. So basically, what I've just shown you here is that a logarithm is basically the inverse of an exponential function. So we've just talked about exponential functions, and now we see that logarithms, our next topic, are just the inverse of that. So what is a logarithm? It's the inverse of an exponential function. So suppose you have a to the x power equals y, then that means log base a of y equals x. So on this one, the x is the input and the y is the output. On this function over here, though, the y is the output and the x is the input, right? Oh, actually, I said that backwards. On this one, the y is the input and the x is the output. Okay, so they switch roles there. Okay, and so that's what a logarithm is. So what I'm going to show you here is we're going to verify each of these equations below by rewriting them in exponential form. Okay, so this probably looks like another language to you. You probably have seen it in Algebra 2, maybe not, I'm not sure. But it's still, logs are always kind of uncomfortable when you first see them because it's just strange looking. But actually, once you to the trained eye, it starts to actually make sense. This number down here is the base. This number out here, which is the output of the log function, becomes the input of the exponential function. And then this number right here, which is the input on the log, is the output of the exponential function. And as you guys can see, 2 to the third power does equal 8, right? Well, that's what this expression is over here. It's just written inversely as a logarithmic expression. So what we've just done is we've proven that this statement is true by looking at an inverse of that, which we understand a little bit better. And that's what we're doing here. We're just rewriting these in exponential form so that we can prove that it's true. So how do we do this again? Whatever number's here, that's your base. Whatever number's here, that's your power. And whatever number is here is your answer, and it should be a correct statement. If this is a true statement, then so is this, because they're just inverses of each other. All right, let's go ahead and check it over here with number 2. So number 2, My base number is 3. The exponent on that 3 will be this number's output, so it'll be -1. And the answer for my exponential function will be the input on my log, which is this 1/3. And this is a true statement as well. 3 to the -1 power means the reciprocal of 3, which is in fact 1/3. So that's a true statement, and therefore so is this. All right, so let's do this one as well. My base is 5 raised to the power of 1/2 equals whatever number is right here, which is square root of 5. And once again, this is something else we should already know. 5 to the 1/2 power is the same thing as the square root of 5. So yes, that's a true statement, and therefore this logarithm expression over here is a true statement. All right, let's go and take a look at the last one here. For this one's a little bit more complicated, but we'll see. We have 3 raised to the 3/2 power equals the square root of 27. All right. Now this may not be obvious to you right now that these are the same thing, but we can mess around with this side a little bit to see if it makes sense to us. So first of all, I'm going to rewrite this as in radical form. In radical form, this 2 goes over here. The base number goes in here, and the power goes as a power on the 3. 3 to the 3rd power is 27. And whenever you're doing square roots, you don't really need to put the 2, so I'll leave that off. And now you guys can see that, yep, those two sides are equal to each other, right? So therefore, this is a true statement, and therefore so is this. So the real skill I want to make sure that you guys know how to do here is how to transform it from log form to exponential form. And then after that, you should be able to make sure that this is true, to make sure that, and that proves that this other side over here is true, all right? So let's go ahead and throw a student practice at you guys. Go ahead and pause the video here, give these problems a try, and when you unpause it, I'll have my answers up. So here's all the expressions written in exponential form. This one's pretty obviously true, right? 5 to the 3rd power is 125. This one's a little bit maybe trickier to see, but 2 to the 3rd power is 8, and since it's negative, it's the reciprocal, so it's 1/8, so that one's true. This one's particularly strange, so let's look at this one here. 2 to the 2nd power is 4, right? But it's negative, so that means it's 1/4. And yes, in fact, 1 over 4 is equal to 0.25, and so we're good there. Last one here. This one's a lot like the last example I did on the example. You're going to rewrite this side in radical form, where you put the bottom number here, the base here, and the power here. And 3 squared is 9, so we end up with the cube root of 9. And therefore, these two sides are equal. So we've proven that those things are true. So we rewrote them in exponential form, and then we just made sense of this and think, is that true? Yeah, so therefore these must be true. All right, so that's what a logarithm is. It's just the inverse of an exponential statement. And so basically, to change a logarithm into an exponential, just ignore the log and switch these two numbers around, and you've pretty much got your problem. 5 to the 3rd power equals 125, right? So there you have it. All right. So let's go ahead and take a look at example 2. On this one, we're going to, instead of me giving you what the log equals, I'm going to ask you guys to figure that out. So what does this log equal? Okay. Well, let's begin. So the first thing we're going to do, I'm going to put an x here because I don't know what log base 2 of 16 is equal to. So I'm just going to say it equals x. But then I'm going to change this into exponential form. I'm going to take my base. I'm going to take this and make it the exponent. And then I'm going to take this number, and that's what this thing should equal. So 2 to what power equals 16? Well, we did this back in chapter 8, the way we solved exponential functions in chapter 8 was we changed these numbers so that they had the same base. So I know I can write 16 as 2 to the 4th power. And then I can drop the bases off and say, okay, cool. X must be 4. So if x is 4, that's what this expression equals. And sure enough, 2 to the 4th power does equal 16, right? All right, let's go ahead and take a look at number 2. Same thing. So the first thing we're going to do is I'm going to make it equal x. And then I'm going to rewrite it in exponential form. It's going to be 3 to the x power equals 1/9. Now to solve this exponential expression, first thing I'm going to do is we learned back in chapter 8 is to change this into a normal 9, but give it a -1 power. Then I'm going to get these bases to match. 9 is 3 squared. Putting those together, we get 3 to the -2. Now that we've got the bases matching, we can drop those bases out and see, okay, x must equal -2, and therefore, that's my answer. Okay, let's go ahead and take a look at number 3. Log base 2 of the cube root of 2. All right, we don't know what that equals yet, so I'm going to put equals x. I'm going to rewrite this in exponential form, so it's going to be 2 to the x power equals the cube root of 2. All right, well, the bases already match, but what I don't like is the cube root there. I'm going to rewrite that cube root as 2 to the 1/3 power. And now I can drop the bases off. I see, oh, okay, x is equal to 1/3, and therefore this must be 1/3. All right, one more. Decimals, this is kind of a new thing. We haven't done this before. In order to do decimals, you kind of have to understand how to change a decimal into a fraction. So how do you do that? Let's talk about that. So to change a decimal into a fraction, you need to understand number places. So what do I mean by number places? I'll just put a bunch of zeros here. This is called the tenths place, right? This one's called the hundredths with a TH. This one's called the thousandths, and so on. This would be 10,000ths. This would be 100,000ths. This would be millionths, etc. So it's just like when we go the other way past the decimals, just that there's no ones place. There's only, it starts with tenths. So it's tenths, hundredths, thousandths, etc. Okay, why is that significant? Well, let's start by looking at the problem we have right now. The last number here is a thousandths number. And so that means I have 1,000th. And so we take the number that we have here, which is 1, and we put it over the number 1,000. And that's how you do it. So before we go on to doing this problem, let me give you another one here. Suppose I had 0.253. Well, that's also, it ends at the thousandths place. So this is 253 thousandths. Or I'll give you another one. Suppose we had 0.25. This one ends in the hundredths place. So I would have 25 over 100. Okay, and yeah, you can reduce these, by the way, which you should if you can. This one actually turns out to be 1/4. All right, so you need to know how to change a decimal into a fraction. So let's begin number 4 here. Log base 10 of 0.001. Okay, step 1 is to change it into a fraction. All right, and then from there we're going to solve it just like we did on the other problems. I'm going to say it equals x. and then we're going to do 10 to the x power equals 1/1000th. And then from there, we don't like fractions, right? Even though we made a fraction, now we want to make it a whole number by making it 1,000, but just raised to the -1 power. The next thing I want to do is I want to get these bases to match, so I'm going to rewrite 1,000 as 10 to the 3rd power. And now we've got a common base there. Simplifying the expression, we have 10 to the x is equal to 10 to the -3. The bases go away, and it turns out we got -3 as our answer. Okay, so that's the idea there. So make it equal x, change it to exponential form, and solve. I'll let you guys go ahead and try some of these here. So go ahead and pause the video here and give numbers 1 through 4 a try. When you unpause it, you'll see the solutions. All right, so here's the answers to numbers 1 and 2. For number 1, log base 4 of 64, you should have gotten 3. And for number 2, log base 4 of 1/16, you should have gotten -2. Here's my work if you guys want to study it. I'm going to go ahead and bring up the answers to numbers 3 and 4 now. All right, so here's the answers to numbers 3 and 4. Number 3, log base 5 of the 4th root of 5 is 1/4. And then the last one here, log base 5 of 0.2 is -1. What I did on this is I changed the 0.2 to be 2/10 because this is 2 and it's in the 10th place, so 2/10. Then I reduced it to 1/5. After that, we change it to exponential form, get the bases to match, and we have our answer. All right, and so there's that. Let's go and move on to our last part. I guess that's it. So we're done for the day. So we'll put this stuff to practice in class next time I see you. Till then, have a good one.